one email regarding the recordings of the lectures. See, you may or may not get the recordings. So why? The reason is that I would insist that you attend the lectures online. Secondly, I am giving you references for each lecture, okay, and as well as the PDF files of the notes. So I would insist that if you cannot attend, then please go through the references. Okay, you may get it, but if at all you get it, then it would be maybe a week or two before the exam, not on a regular level. So g of f is 1 upon 2w g of delta f for minus f x. So this is important. So GFF is band limited. Okay. Now we said band limited means that g of f is non-zero. Now g of f, I would say that mod of g of f should be the case is non-zero for f lying between w and minus 2. Okay. Or you can simply even say that g of f is non-zero for. Otherwise, g of f can be a complex number as well. Generally, the Fourier transforms are complex. So whatever we are drawing is mod of g of f. Okay, you should remember that. But I think we are considering. Okay, we have not yet said anything about whether g of t is. Although we are considering a real waveform, so if at all the signal is real, then the Fourier transform has some properties that it is conjugate symmetric and all this. Let us leave this. Assume that mod gf is 0 for non-zero for minus w to w. So in that case, and if my sampling frequency is equal to 2, then I can write this. Okay, that g of f is 1 upon 2w, g delta f. This 1 upon 2w occurs because in g of delta f, you have a scaling of 2w. Let me write it down so that if at all when you will be revising, you know that why this factor comes. Because sometimes in interviews this is asked that why does this factor comes. So in g of delta f, g of f gets scaled by 2. Okay. So, or sorry, f of s is what is the scaling factor. But here since f of s is 2w, so I am writing it w. Okay. Now one more thing, that using the Fourier series, for g of delta f, we can note that this can be written as g of f can be written as 1 upon 2w summation n is equal to minus infinity to infinity g of n by 2w e raised to power minus j pi n f divided by 2. Okay. Now remember that this can be written, we can using this over, this is important to write, because otherwise g of f is 0 elsewhere. You should remember that we have said that g of f is band limited. So this mod of g of f exists only for minus w plus w. Okay. So using the two equations, let me make you see the two equations. So these are the two things which we have used. One is this is the Fourier series representation of g delta f, and another one is the shifted spectrum. Okay, using both of them, we write this. So with this as an observation, let us write one reason, okay, which will allow us tell something about sampling. So therefore, I am writing it down. If the sample values, therefore, if the sample values g of n by 2w of a signal g of t are specified, for all n, suppose you know this, then Fourier transform g of f of the signal is uniquely determined, you can say, by using discrete time Fourier transform or of 6. Okay, let us say this I number is 6. Okay, so you can see that this g of f, which is the Fourier transform of the original signal, is unsampled signal. So I can write it as this. Okay, now in this is nothing but a Fourier series or discrete time Fourier transform, where I am evaluating the discrete time Fourier transform of the samples of the ओरिजिनल सिग्नल और द अनसैम्पल्ड सिग्नल का जो सैंपल्स लिया मैंने उसके हेल्प से आई एम कैलकुलेटिंग दिस डिस्क्रीट टाइम ट्रांसफॉर्म एंड द डेवलपमेंट सेज दैट ओवर दिस इंटरवल माइनस w to w this DTFT is nothing but the Fourier transform. So this observation gives us the underlying principle of sampling theory. Now GT and G of f are related through inverse Fourier transform. Okay, this we know that G of t and G of f are Fourier transform pair. It means G of t is Fourier transform is G of f, and if I evaluate the inverse Fourier transform G of f, it will definitely come out to be G of t. Now this is one property which is covered, taught, or maybe forms a part of signals and systems. I think you must have gone through it. Anyways, we do not have time to go to this property, but we can state this, that we know that if at all I evaluate the Fourier transform, inverse Fourier transform of G of f, I will definitely land with G of t. I won't be landing it with a different function. Okay, uniqueness sort of a property is there. Now, G of t. So now we can see that if your G of f can be determined by the sequence G of n by 2w, and G of t can be determined by G of f. So I can say that G of t is itself uniquely determined by the sample values G of n by 2w for all. Okay, let us see. So G of f, let me write it like this. We can see that G of t can be obtained from G of f by inverse Fourier transform, and G of f can be directly obtained or approximated, whatever you say, from the sample values n line between infinity to minus 1. Okay. So if at all G of n by 2w determine G of f, and G of f we can directly use the inverse Fourier transform operator to find G of t. So we can simply say that G of n by 2w will uniquely determine G of t. So that was our starting point, that whatever sampling procedure we adopt, the samples should give me the original signal uniquely. It means if I try to recover from G of n by 2w my G of t, it should be land up with G of t only. It should not be a different function. So this thing we can write like this also, that sequence G of n by 2w has all the information contained in G of t. Okay, so this is pretty much the development behind saying that you should sample at the Nyquist frequency. Nyquist frequency is simply for a band limited signal twice of the frequency span. It means कि minus w से w, जो w if you say as the positive bandwidth, so twice of w should be the sampling rate minimum, so that these samples can uniquely determine G of t. Now up to now we have not said how to recover. So now the question is, first of all, how to. So this is done. Okay, The development behind 2W is now done. So we know that why we need to sample at a rate which is at least 2W or greater than 2W. Okay. Now the question is how to recover. How to recover / reconstruct. Okay. How to reconstruct G of t from the sequence G of n by 2W. How to do it? Okay. Let me check if there is anything. So for this, we will do a small development. Let us take a new page for that. So we know that G of t is nothing but the inverse Fourier transform of G of f. We know this. So I am writing it for you. 2 pi ft dt, and this will go from minus infinity to infinity. This is the standard inverse Fourier transform relation, okay, between G of t and G of f. Now I can write G of t like this: minus w to w 1 upon 2w. Now reason being that G of f was band limit. Okay, so G of f exists only from minus w to w, and using this equation over this range, I can express G of f as this. It means that I can, for the range, it is important to say that for the range this, I can very well write it GF like this. So we substitute it here, summation n is equal to minus infinity to infinity, G of n by 2w e raised to power minus j pi nf by w e raised to power j 2 pi ft dt. Now in this interchange, now since integration or integral is a linear operator, we can interchange. So interchange order of summation, and integration. Okay, so what we will get, that G of t is simply summation n is equal to minus infinity to infinity G of n by 2w 1 upon 2w integration minus w to w e raised to power j2 pi f t minus n by 2w df. Okay. So now for those, I would encourage all of you to just sit with a pen and paper in classes where a bit of analysis is done. So I would give you 2-3 minutes. Can you evaluate this integral for me? Very, very simple integral. I think you must have done it earlier as well. So please evaluate this integral and tell me what is the answer. I will give you 2 minutes. Right now it's 8:55. You will start at 8:57 or 8:58. Otherwise I will derive it anyway. So all of you, or at least those of you who have a pen and paper around you, please try doing this. Very simple, result is there. Okay, so we have 168 attendees today. So at least 40% must be sitting with pen and paper. This is my assumption. Please try doing this. If anyone gets an answer, you just unmute and say, what will you get? Remember that this is an integration with respect to f, not t. So let me just give you the result. Those who are trying, they may confirm it. So the result is, I am not evaluating it, I am giving you the result. The final result is sine of 2 pi wt minus n pi upon 2 pi wt minus n pi. So this is the result. See, this is very simple to do. I do not think that I should spend some time evaluating it, but I want if at least one or two of you have done it, then it would be great. You can respond saying that yes, we could find this out. No one is able to do it. No, this cannot be the case. Okay, so this is left as a small homework. It means that while reading, you need to derive it yourself. This homework is not for submission. This is just a simple homework, meaning that once you are reading the notes, you should do it. So this is nothing but the sinc function. Okay, this is the sinc function where the definition of sinc function, I will write it down because there is no uniformity in defining sinc. Sometimes people use pi there and sometimes they don't. So what we will be using, I will write it down. This is 2wt minus n. Okay. This is g of t. So we have used sinc as sinc of x as sine of pi x upon pi x. That is what we have used. So you separate pi from the argument of sine and similarly from the denominator, and you will get this. Now this says that for minus infinity t line from minus infinity to infinity. See, above n is a discrete, n is an integer. Okay, if I write n line from minus infinity to infinity, n will take integer values, but here t is a real number. Okay? So it will take any value from minus infinity to plus infinity. So we see that g of t can be written in terms of the samples with the help of sinc. Okay? So what is the interpretation for this? So this was the so this is the interpolation formula. So this is the interpolation formula. Okay, for reconstructing the original signal gt from sequence of samples sample values. I think sample values should be a better term to use here. Use g of n by 2w with sinc function as the sinc function sine of 2wt, sinc of 2wt as the interpolation function. Okay. Now, what are we? And if at all we see this equation, then what are we doing is, let me write it down. So you delay sync by the integer number. Yes. Somebody wants to say something? No. I thought that I think somebody unmuted. तो delaying, yes. Yes, somebody wants to say something. I think somebody is on unmute. Yeah. So if there is any issue, you can just type it in the chat window as well. There's no issue. Okay. So you delaying, multiply with the sample value and add. Multiply with corresponding sample value and finally add to get g of t. So these are the three operations which we do to recover g of t from g of n by 2w. Now this is a sort of an ideal interpolation of an ideally sampled signal. Okay. So let me write it down. I think this is ideal interpolation for ideally sampled band limited signal g of t. Note that this is physically realizable. This you will find written at a lot of places. Now, physically realizable means that it has finite energy and few of the properties which the Fourier transform should satisfy. Let us say a signal should satisfy to have a valid Fourier transform. This must satisfy. So ऐसा नहीं है कि हमने g of t लिख दिया तो सिर्फ बैंड लिमिटेड ही है. बट हाँ, जब आप लोग जनरली इफ यू विल टॉक इन टर्म्स ऑफ यूसेज या आप जब यूज करेंगे आपसे पूछा जाएगा तो कोई ये बोलेगा नहीं कि g of t जो है वो फाइनाइट एनर्जी है या g of t जो है वो प्रॉपर्टी सेटिस्फाई करता है जो कि उसको फूरियर ट्रांसफॉर्म एग्जिस्ट करने के लिए होना चाहिए. इट विल बी इम्प्लिसिट बट ये वैल्यू होल्ड करती है बात की g of t को ऐसा होना चाहिए तभी whatever we have done is valid. Now let us write the sampling theorem. It's just a two statement thing. So this is the sampling theorem. Okay. For strictly band limited signals, now this is important. For strictly, this word I think I mentioned in the first class or maybe in the second class. For strictly band limited signals, it means it should not have any component higher than W hertz. And limited signals of finite energy. What is the meaning of this? Let me write it down. No component higher than W hertz. Okay, this you must know. So there are two ways to write this. So one way is such a function slash signal is completely described by values separated in time by 1/2W seconds. Okay. And another equivalent form, equivalently. So I am writing equivalently means either you can say 1 or you can say 2. It can be recovered from knowledge of examples taken at the rate of 2W samples per second. So this is simply stating this in terms of T s, and here I will write. So this refers to T of s, and this refers to f of s, and they are inversely related to each other. So this is just an equivalent way of saying. Now you will find a proper way of writing the sampling theorem as well in the text, but the underlying principle is what we have just studied and what we have just said. Okay, so this can be pictured properly as a theorem as well. So you will find, if at all you find this, do not feel that you have not studied it. This is what is the crux of it, and you can state it in a different sense as well. You can write it more properly. We have followed Hakings for this, so this our textbook has mentioned it this way. So to be consistent with what we are doing, I have written it from there directly. Okay. So Nyquist rate. So we define that. So after doing this, it is important to define that what is a Nyquist rate, or 2W is called as the Nyquist rate. Nyquist rate is 2W samples per second. Okay. And Nyquist interval. So there are two terms. Interval means that interval between two samples, that has to be 1 upon 2W seconds. Okay. And I think this is in conjunction with this assumption that this Nyquist rate and Nyquist interval, at least theoretically, is defined for strictly band limited signals. Okay. So we are done with the sampling theorem, which we did from Simon Haking, and I have clearly mentioned the section in the lecture break of 5 in the class drive. Now we will go towards another development or another possibility, which is very, very interesting to find out. Okay, so this we will be covering from Leon Couch's book. Okay, and this, why I am covering, is that when I was an undergraduate student, if at all these things were left, no, so later on we used to feel basically later on we were left in problem, because sometimes in interviews for master's programs or in interviews for companies, people do ask these things, and if we have not studied, we are lost. So I thought of mentioning one important property of sinc function, that is that it forms the basis for continuous time signals. Okay, so this is important to mention here, because here we will prove the orthogonality of shifted sincs. That is important. That sinc function, when shifted by a proper shifting parameter, it is orthogonal. Okay, so let's see this. So we will now go to sampling theorem. A different view. Okay, so I am mentioning it in the notes as a different view, or a view in which at least Claude Shannon solved. Okay, so I think I mentioned it that in 1948 he wrote a paper in which he laid the foundations for digital communication. He said that any sort of a source can be encoded in a digital sequence, and that digital sequence can be reliably transmitted over a noisy channel. Noisy means that a channel which adds noise to the transmitted data. So while doing that, he basically referred to this sampling theorem which we are going to derive. Okay? He argued in the way in which we are going to write it down. Okay? So first we will mention this. So any physical, note that we are not covering anything which is not to be covered at the UG level. This is from the book. I think, let me write it down. This is DAC, Digital and Analog Communication System, by Couch. This is a book which is generally followed at undergraduate. Okay, Couch 2. So we are picking it from there. So any physical waveform can be represented over the interval minus infinity less than t less than infinity pi. Okay, so WT is equal to summation n is equal to minus infinity to infinity a of n sine of pi fs d minus n by f of s on. This is nothing, this is basically sinc function, okay? Where E of n is equal to f of s minus infinity to infinity w of t sine of. I think this type of an equation or concept you must have come across. This is the basis expansion, okay? I think this basis, but at least you know by now. D minus n by f of s. Okay, this is d of t. Let us write down the result first, and then we will discuss. And f of s is a parameter that is assigned. So I'm exactly quoting the textbook. Assigned some convenient value greater than c. Okay, so right now we have not said anything about this f of s. We are saying that it is some value which is greater than 0. And in terms of this, we can write any physical waveform. Physical waveform, I think I have said it several times what it means. So it can be represented over minus infinity to infinity via this series. Okay, this is not a sequence. A of n is a sequence, and this summation is a series. Okay, so we can represent it as this series. Now we have not said anything about whether A and are the sample values of WT. You will see that now. I will write it down that in what condition these A of n are nothing but the sample of WT. Furthermore, now let us write down the main thing. Furthermore, if WT is band limited to P and f of s is greater than equal to 2p, then so right now notice that we have not said that f of s is equal to 2p. We are saying f of s needs to be greater than equal to 2p. Then let me write it down as this is equation suppose 7 and this is suppose 8, because we started equation numbering from 6 to this. But then 7 becomes the sampling function representation. Where A of n is equal to W n by s. Okay. Let me use a small W. Okay. That is for f of s greater than equal to 2W, so 2p. Okay, so why I think I need to mention one very important thing here, that since we have changed the textbooks, there is a problem. So Simon Hakin used W as the highest value of the frequency, which has a non-zero component, but here that is B. Okay, so you have to, I think, take care of this notation while we move from one book to other. In a way, that is good as well, because then we need to focus on the concept instead of mugging things up. And viewed differently, this can be a nuisance as well. But I think I cannot help much in this regard, because if at all we go on changing the notations, it will take a lot of unnecessary time. And at this stage, in 5th semester, I can assume that you can easily work it around. Okay, that is for fs greater than equal to 2 be the orthogonal series coefficients are simply the values of samples when W is sampled every okay. So this is the result. If at all, I will just say to you that initially we started from that, let us say over the interval minus infinity to infinity, we write Wt. This is a physically realizable waveform, a physical waveform, as this series. Okay? And where we said that the coefficients of each sinc function can be obtained by the projection of this function on that function, Wt on that particular sinc function. Now, I think you generally study groups and linear algebra and all these courses. So there you will go through the definition of basis functions and how do you obtain the corresponding coefficients of the basis functions in the series representation of a particular function. Or, yes, somebody unmuted. You need to say something. Okay. So there you will go through it. Okay, definitely. So that's why I am skipping it here. That component of linear algebra, I assume, is being covered in some other course. Then why should we put up time on it? We should now study some applications. So this is one of the applications that we can write Wt like this. So a of n can be obtained by integration of that function Wt with that particular basis function, or here it is a particular sinc function. So see this. So here this summation is over n, but here this n is fixed. So for a particular basis function, that is with respect to n, we are doing this integration. This fs is a scaling parameter, remember this. So we said that we can write Wt like this, where fs is some parameter which is greater than 0. Now one observation is that if at all my Wt is bandlimited to GHz, and if my sampling rate, that is f of s, sorry, right now we have not yet said that fs is a sampling rate, we are simply saying that if f of s is greater than equal to 2p, then your a of n becomes w of n by fs. Now this is very important. So this says that I can represent Wt in terms of its samples. Okay. So this was basically the cardinal series. This is what this was. This is known from 1915. Okay. So from 1915, people know this, that this is the cardinal series. This is a better development. It is, you can say that this was further developed, or further observation was made that if at all Wt is band limited to p hertz and f of s is chosen as greater than 2p, then this a of n becomes your samples of the function itself. Okay. So we say that is for fs greater than or equal to 2b, the orthogonal series coefficient. So this is an orthogonal series. Why? Because for each n, let us say if I choose n as 2 and if I consider n as 3, so the corresponding sinc functions for n as 2 and n as 3 will be orthogonal. We will show it. We will prove it. Okay. So that is for fs greater than 2b. The orthogonal series coefficients are simply the values of samples when w is sampled every 1 upon fs series. Okay. So we can now go ahead and prove it, but let us first see. So we will prove it, and here we will observe one important thing, that the sinc functions are orthogonal. Okay. So I could have stated this result without proving, but this proof involves one very important result, which is the core of digital communication. And sinc functions you must know if you are undergoing courses on analog and digital communication. This is a very, very important, at least theoretically, category of functions which we must know. Okay. So let us first show that phi of nt, which is equal to sine of pi of fs t minus n by fs. Okay. Let us first form a set of the orthogonal form, a set of orthogonal okay. For this, what we need to show is that minus infinity to infinity phi of nt into phi of nt star dt is equal to k of n delta of n. Okay. Now let us see that what do we mean by this. Let me write it down first. So it means that this is, if I write it more clearly, that this is equal to k of n for n equal to m and 0 for n naught. Because this is what is definition of delta in n function. Basically, this is 1 if n is equal to m, and this is 0 if n is not equal to m. So using that definition, we write it. So if at all my m is equal to n, then this gives me a non-zero value. If at all my n is if n is equal to m, I get a non-zero value, and if n is not equal to m, I get 0. And this should be true for all n m, for all n comma n pairs. Okay. So if this is satisfied by phi and t, then they form a set of orthogonal functions. Now you directly cannot show it easily. Okay, this is one of a very good questions which is given, and if you try working it in time domain, then in the first go you cannot derive it. Okay, so we will use Parseval's theorem to derive it. So using Parseval's theorem, so here another application of what we studied in signals and systems. So we are taught Parseval's relation or Parseval's theorem there. So using Parseval's theorem, we can write this like this. Phi of nf to phi of m star f. That is, this sort of a multiplication and integration can well be performed in frequency domain or after taking the Fourier transform of each of the functions. Okay, so this can be done in this, and the value which it takes is same. So where, I think, let me write it down for completion, that where phi n of f is nothing but the Fourier transform of phi n t, and similarly phi m f nothing but the Fourier transform of phi n. Now let us sink of or sine of pi fst divided by pi fst, which is equal to sink of fst. The Fourier transform is 1 upon f of s, so f by f of s. Now what is this? So this is the rect function. Okay. So what I am doing is that I am not writing the definition of the rect function. I think it should be clear. Basically, this is what this will take value. I think 1 for minus fs by 2 to fs by 2. So this is the pictorial representation of this rect function. So I mentioned that this is a rect function. So now shift t by n by fs. If we do that, then think of fs into t minus n by fs. That is, we knew. Let us say हमें पता था कि sinc fst का क्या Fourier transform है. So if at all we shift it, now what I have done is that I have shifted this t by n by fs. So using the identity or the properties of Fourier transform, so there is another application also what we have studied. We get that this will be now 1 upon f of s. So this equality means over Fourier transform is valid. Okay, I'm just drawing here. Otherwise this can invoke some confusion. 1 by fs pi of f by fs e raised to power minus j two pi nf by fs. Okay. So, now with this as the case, now let us evaluate this integration. Okay? So we know what will be phi nf and everything. So let me give the number as 9. So putting it in 9 or evaluating 9, putting the above result in 9. So 1 upon fs square integration minus infinity to infinity by f by fs whole square e raised to power minus j 2 pi n minus m f by fs df. Okay. I have simply just substituted for n and m. This is equal to, now these two functions, this function pi of f by fs only takes a non-zero value for minus fs by 2 to fs by 2. So I can write it like this. Minus fs by 2 to fs by 2 e raised to power minus j 2 pi n minus m f by fs df. So now we can take another 2 to 3 minutes of break, in the sense that, can you tell me what is the result of this integration? This is a small exercise. This is a classroom exercise, you can call. So I will give you at least 3 minutes. We will start maybe at 9:34. So you can just do it and tell me that what is the result you get. Those who have a pen and paper, please do try. This will give you a good understanding of what we are doing, as well as sharpen up your concepts. If anybody is able to do it before time, please unmute and tell what did you obtain. Yes, no one is able to do it. So this cannot be the case. We have 141 attendees right now, and no one is able to do it. It is not possible because this is very simple. So let me tell you the result. I think maybe some of you are trying, but are stuck in between or still completing it. So the result is, particularly for this integration, the answer you get is f of s delta of n. Okay. Let me derive it for you. So this is like e raised to power minus j 2 pi n minus m f upon fs is to be divided by minus of j 2 pi n minus m by fs. Okay. And then you have to put minus fs by 2 to fs by 2. So now at least you can try putting in, checking that what do you get. It is to power minus j 2 pi n minus m in fs by 2, so it's 1 by 2, so pi is gone. Minus e raised to power minus j 2 pi n minus m. This is again 1 by 2 with a plus sign. Okay. And divide by minus of j 2 pi n minus m upon fs. Now you can do it. Okay. If at all this is not done, if at all you are not able to do it, then we can discuss it in the next class or in subsequent classes. If at all you do it towards the end of the exam and still you are not able to evaluate it, you can tell me, then I can discuss it completely. So after this, I leave it as homework. Try to do it. And these homeworks which I am leaving, they may form part of mid-sem and end-sem exams. Okay, remember that they are not homeworks to be left in lurch. You need to do it. So let us visit one small concept before we move ahead in deriving, that if at all you have f of ss2b, then you will get an as the sample values of the original signal. Let us revisit one concept. So functions, I think I've written it. Let me write it more formally then. Functions phi nt and phi nt are said to be orthogonal with respect to each other over the interval if they satisfy the condition. Integration a to b phi nt, that I think I have already mentioned it for infinity to infinity, but for the sake of completion I need to mention this because I need to write one thing after this. said to be, until they satisfy the condition, they are called orthogonal functions. They are called orthogonal. If, or further, if A to B, phi and T, phi and T, Tt is equal to 0 for n not equal to m, it is 1 for n equal to m, they are called orthonormal functions. I think this orthogonal and orthonormal concept, I assume that you must have gone through. Basically, orthonormal means that the norm of each function, or let us say if I assume that n is m. So basically I'm saying that A to B must be, that is the energy of phi and T must be 1. Although it can be any number k of n. So if it is k of n, then you have to scale each function by root of k of n. Means it is a possibility that here you get the result as k of n. And if you scale phi and t and phi of mt with respect, or sorry, phi and t with its norm, that is divided by the root of it, then you will get as 1 the result of this integration. So then you can convert an orthogonal set to an orthonormal set. You just delete it. So I think for today we can stop at this point, because I need to write 2-3 important things after this, and I won't be able to complete in another 5-7 minutes. I need to do it in the next class. So if you have any issue, any doubt, you can just unmute and say. Otherwise, we are done for the day. Okay, somebody replied. Oh, you could have unmuted yourself. Siddharth Rathod. Thanks. Good. I think you have written it to be 1 by Fs. It should be Fs. Okay, all of you try, but at least you responded. So for that, I am appreciating you. You could have unmuted and said. So okay, we'll meet on Friday, 10:15.